Okay, now let's look at step number 2. Okay, so step number 2 is that we express our initial state psi of I, not to be confused with psi of the wave function in region 1, as a linear combination in terms of psi k. So we express this, and the way we do this is that we have some distribution, some momentum distribution, and let's call that A of K1 D of K1. Okay, so we know this, so we just have to find this. Okay, so this is just nothing but the generalization of the formula that I can express any all wave function as a linear combination of the energy eigenstate. Okay, but if the energy eigenstates were discrete, then the sum would be discrete. If the energy distribution is continuous, then the sum would be an integral. And that's why we have an integral here. So these A's are nothing but the CI's. Okay, is that clear?
Yeah, makes sense.
Okay, so what are these AI's? So A of K1 is, according to our quantum mechanics, is just the inner product between the eigenstate and the initial state, right? But using the orthogonality of the momentum eigenstates. Okay, so this is, so now let's just compute this. So this is psi of K1 psi of I is going to be, there's an A here, and the A comes from this guy, and we choose A to be real, so we don't have A star or stuff like that. Actually, I think we should have A to be, just 1 second. Yeah, I think A should be, yeah, it should be A star. Yeah, that's not very important. Okay, so inside we have integral of e to the power minus I k1x plus b by a star e to the power plus I k1x times theta of minus x multiplying psi I of x dx. Okay, so this is this, if I go back, this is this guy. Okay, what we're doing is that we're taking the complex conjugate of this thing and multiplying it this. So that's the first term. And the second term is going to be integral between minus infinity to plus infinity, then c by a star, and e to the power minus I k2 of x. So k2, we are using k2 as a shorthand. We know how to express k2 in terms of k1. So theta of x, psi of x. Okay, so this is nothing new here. We are just putting in the value of psi of k1. Okay, so this is not a very hard integral to evaluate. Okay, so now note that psi of I of x, the initial wave function at time 0, has support only on the left side of the potential step, right? So so that means that psi of I of x is 0 when theta of x is 1. So that means that this integral is going to give me 0, because here we have this is where this is positive, this is 0, and vice versa. Okay? So we are left with these two integrals. So the second term, like this term, can also be shown to vanish. And why is that? The reason for this is that if you look at psi of I contains sum over momentum modes, which if you evolve them in time, they travel to the right. Whereas this thing is a momentum mode. If you evolve it, it is something that is traveling to the left. Right? And therefore, when you take the inner product between these two things, what will happen is that their momenta, even if their values overlap, their signs will not overlap. Their signs will be different. And therefore, the integral would give you 0. Okay, so we can also, ignore this guy. Okay. Also,
I didn't
you should think
understand
what.
this one, I think.
Right. Okay. So what is this? This is this involves a bunch of momentum modes which are traveling to the right. It's a Gaussian distribution, but we can think of it as a linear combination of momentum modes traveling to the right. Okay. So
Okay.
they have in the right. So so they have in them factors. So you have a integral over momentum, but you have factors like e to the power I some k of x, right? Now, so you can if I what do I have? I have if I have e of k a momentum mode and e of k prime, then the inner product is 0, right?
Oh, I see. So k and k prime will never be equal, so it'll always give you 0.
Exactly, yeah. And this guy is just 1, over those region. So that's why it's going to be 0. It's by orthogonality. Okay. So at the end, we have an expression for a of ak1. So ak1 is going to be some normalization factor from minus infinity to plus infinity, e to the power minus I k1x, and then the initial Gaussian, which is e to the power I k0 x plus a e to the power minus I. It's not, yeah, there's no I here, right? there's no I here, e to the power minus x plus a whole squared divided by 2 delta squared into d of x. Okay, so this is what we have as a okay, is it clear what? So there's also a factor of, say, theta of minus x, but we can ignore this because this is 1 whenever psi I is peaked, is non-zero, where psi I is 0, this guy is 0 anyway, so we can actually ignore this, right? This is just 1. So in the region of interest where this integral is non-zero, this guy is 1. So we can ignore that. Okay. Any questions? Okay, now we can, shift the integral from x to x minus a, and we are allowed to do that. That's a symmetry, and then it's just some constant. Then we get n e to the power plus I k1 of x of a, sorry, k1a, and inside the integral I get e to the power minus I k naught, sorry, k1 minus k naught, k1 minus k naught x e to the power minus x squared by 2 delta squared of dx. Okay, so this is a Gaussian integral. And if you do the Gaussian integral, we get a of k1. And if we normalize stuff, then we get delta by square root of delta by square root of pi e to the power I k1a, and then e to the power minus k1 minus k naught squared del squared by 2. Essentially a Gaussian on momentum space. And this is exactly what we expected, okay? So this is how we find AK, and that is, once we have found AK, we have expressed our initial state as a linear combination of the energy eigenstates, okay? So the step 3 is now to look at what this wave function looks like when you evolve it forward in time. And that's something we will do in the next class. Okay? Any questions?
No, sir.
Okay. All right. In that case, have a good day, and